In geometry, a torus is a surface of revolution generated by revolving a circle in three-dimensional space about an axis coplanar with the circle. If the axis of revolution does not touch the circle, the surface has a ring shape and is called a ring torus or simply torus if the ring shape is implicit. When the axis is tangent to the circle, the resulting surface is called a horn torus. When the axis is a chord of the circle, it is called a spindle torus. A degenerate case is when the axis is a diameter of the circle, which simply generates a two-sphere. The ring torus bounds a solid known as a toroid. The adjective toroidal can be applied to tori, toroids or, more generally, any ring shapers in toroidal inductors and transformers. Real-world examples of toroidal objects include doughnuts, vadais, inner tubes, bagels, many lifebuoys, O-rings and vortex rings. In topology, a ring torus is homeomorphic to the Cartesian product of two circles, S1AA, or S1, and the latter is taken to be the definition in that context. It is a compact two-manifold of genus 1. The ring torus is one way to embed this space into three-dimensional Euclidean space, but another way to do this is the Cartesian product of the embedding of S1 in the plane. This produces a geometric object called the Clifford torus, a surface in 4 space. The word torus comes from the Latin word meaning cushion. Geometry. A torus can be defined parametrically by where I are angles which make a full circle, starting at 0 and ending at 2i euro, so that their values start and end at the same point. R is the distance from the center of the tube to the center of the torus, r is the radius of the tube. R and R are also known as the major radius, and minor radius, respectively. The ratio of the two is known as the aspect ratio. A doughnut has an aspect ratio of about 2 to 3. An implicit equation in Cartesian coordinates for a torus radially symmetric about the z-axis is, or the solution of f, x, y, z, equals 0, where algebraically eliminating the square root gives a quartic equation. The 3 different classes of standard tori correspond to the 3 possible relative sizes of R and R. When R, the surface will be the familiar ring torus. The case R equals A corresponds to the horn torus, which in effect is a torus with no hole. The case R describes the self-intersecting spindle torus. When R equals 0, the torus degenerates to the sphere. When R per million R, the interior of this torus is diffeomorphic to a product of an Euclidean open disk and a circle. The surface area and interior volume of this torus are easily computed using Pappus's centroid theorem giving. These formulas are the same as for a cylinder of length 2i euro r and radius r, created by cutting the tube and unrolling it by straightening out the line running around the center of the tube. The losses in surface area and volume on the inner side of the tube exactly cancel out the gains on the outer side. As a torus is the product of two circles, a modified version of the spherical coordinate system is sometimes used. In traditional spherical coordinates there are 3 measures, r, the distance from the center of the coordinate system, and I, angles measured from the center point. As a torus has, effectively, 2 center points, the center points of the angles are moved. I measures the same angle as it does in the spherical system, but is known as the toroidal direction. The center point of I is moved to the center of R, and is known as the poloidal direction. These terms were first used in a discussion of the Earth's magnetic field, where poloidal was used to denote the direction toward the poles. In modern use these terms are more commonly used to discuss magnetic confinement fusion devices. Topology. Topologically, a torus is a closed surface defined as the product of 2 circles, S1AA, or S1. This can be viewed as lying in C2 and is a subset of the 3-sphere S3 of radius h2. This topological torus is also often called the Clifford torus. In fact, S3 is filled out by a family of nested tori in this manner, a fact which is important in the study of S3 as a fiber bundle over S2. The surface described above, given the relative topology from O3, is homeomorphic to a topological torus as long as it does not intersect its own axis. A particular homeomorphism is given by stereographically projecting the topological torus into a 3 from the north pole of S3. The torus can also be described as a quotient of the Cartesian plane under the identifications, x, a euro y. Or, equivalently, as the quotient of the unit square by pasting the opposite edges together, described as a fundamental polygon of R1 bar 1. The fundamental group of the torus is just the direct product of the fundamental group of the circle with itself. Intuitively speaking, this means that a closed path that circles the torus hole, and then circles the torus body can be deformed to a path that circles the body and then the hole. So, strictly latitudinal and strictly longitudinal paths commute. This might be imagined as two shoelaces passing through each other, then unwinding, then rewinding. If a torus is punctured and turned inside out, then another torus results, with lines of latitude and longitude interchanged. The first homology group of the torus is isomorphic to the fundamental group. Two-sheeted cover, the two torus double covers the two-sphere, with 4 ramification points. Every conformal structure on the two torus can be represented as a two-sheeted cover of the two-sphere. The points on the torus corresponding to the ramification points are the Weierstrass points. In fact, the conformal type of the torus is determined by the cross ratio of the 4 points. N-dimensional torus. The torus has a generalization to higher dimensions, the n-dimensional torus, often called the n-torus or hypertorus for short. Recalling that the torus is the product space of two circles, the n-dimensional torus is the product of n circles. That is, the one torus is just the circle, T1 equals OS1. The torus discussed above is the two torus, T2. And similar to the two torus, the n torus, Tn can be described as a quotient of Rn under integral shifts in any coordinate. That is, the n torus is Rn modulo the action of the integer lattice Zn. Equivalently, the n torus is obtained from the n-dimensional hypercube by gluing the opposite faces together. An n torus in this sense is an example of an n-dimensional compact manifold. It is also an example of a compact abelian Lie group. This follows from the fact that the unit circle is a compact abelian Lie group. Group multiplication on the torus is then defined by coordinate-wise multiplication. Toroidal groups play an important part in the theory of compact Lie groups. This is due in part to the fact that in any compact Lie group G1 can always find a maximal torus. That is, a closed subgroup which is a torus of the largest possible dimension. Such maximal tori T have a controlling role to play in theory of connected G-toroidal groups are examples of protori, which are compact connected abelian groups, which are not required to be manifolds. Automorphisms of T are easily constructed from automorphisms of the lattice Zn, which are classified by invertible integral matrices of size n with an integral inverse. These are just the integral matrices with determinant a plus or minus 1. Making them act on Rn in the usual way, one has the typical toral automorphism on the quotient. The fundamental group of an n torus is a free abelian group of rank n. The kth homology group of an n torus is a free abelian group of rank n choose k. It follows that the Euler characteristic of the n torus is 0 for all n. The cohomology ring H Tn, a Z, can be identified with the exterior algebra over the Z module Zn whose generators are the duals of the n non-trivial cycles. Configuration space. As the n torus is the n-fold product of the circle, the n torus is the configuration space of n-ordered, not necessarily distinct points on the circle. Symbolically, Tn equals n. The configuration space of unordered, not necessarily distinct points is accordingly the orbifold Tn-Sn, which is the quotient of the torus by the symmetric group on n letters. For n equals 2, the quotient is the Mar paragraph bias strip, the edge corresponding to the orbifold points where the two coordinates coincide. For n equals 3, this quotient may be described as a solid torus with cross-section and equilateral triangle, with a twist. Equivalently, as a triangular prism whose top and bottom faces are connected with a 1/3 twist, the three-dimensional interior corresponds to the points on the three torus where all three coordinates are distinct, the two-dimensional face corresponds to points with two coordinates equal and the third different, while the one-dimensional edge corresponds to points with all three coordinates identical. These orbifolds have found significant applications to music theory in the work of Dmitry Tymochko and collaborators, being used to model musical triads. Flat torus. The flat torus is a torus with a metric inherited from its representation as the quotient, R2 per liter, where L is a discrete subgroup of R2 isomorphic to Z2. This gives the quotient the structure of a Riemannian manifold. Perhaps the simplest example of this is when L equals Z2 itself, R2/Z2, which can also be described as the Cartesian plane under the identifications. This particular flat torus is known as the square flat torus. This metric of the square flat torus can also be realized by specific embeddings of the familiar two torus into Euclidean 4 space or higher dimensions. Its surface has zero Gaussian curvature everywhere. Its surface is flat in the same sense that the surface of a cylinder is flat. In 3 dimensions one can bend a flat sheet of paper into a cylinder without stretching the paper, but you cannot then bend the cylinder into a torus without stretching the paper. A simple 4-dimensional Euclidean embedding of a rectangular flat torus is as follows: x, a euro y, a euro z, a euro w, equals, where r and p are constants determining the aspect ratio. It is diffeomorphic to a regular torus but not isometric. It cannot be isometrically embedded into Euclidean 3 space. Mapping it into 3 space requires you to stretch it, in which case it looks like a regular torus. For example, the following map, x, ay, az, equals cos, u, a, r plus sin, v sin, u, a pcos, v. If L and p in the above flat torus form a unit vector r, p, equals cos, I, sin, I, then u, v, and I can be used to parameterize the unit 3-sphere in a parameterization associated with the Hopf map. In particular, for certain very specific choices of a square flat torus in the 3-sphere S3, where I equals I euro/4 above, the torus will partition the 3-sphere into 2 congruent solid tori subsets with the aforesaid flat torus surface as their common boundary. One example is the torus T defined by T equals S3x2 plus y2 equals 1/2, z2 plus w2 equals 1/2. Other tori in S3 having this partitioning property include the square tori of the form QAT, where Q is a rotation of 4-dimensional space of 4, or in other words Q is a member of the Lie group SO, 4. It is known that there exists no C2 flat torus into 3 space. On the other hand, according to the Nash-Cooper theorem showed in the 1950s that an isometric C1 embedding exists. This is solely an existence proof, and does not provide explicit equations for such an embedding. In April 2012, an explicit C1 embedding of a flat torus into 3-dimensional Euclidean space A3 was found. It is similar in structure to a fractal as it is constructed by repeatedly corrugating a normal torus. Like fractals, it has no defined Gaussian curvature. However, unlike fractals, it does have defined surface normals. It is a flat torus in the sense that as metric spaces, it is isometric to a flat square torus. This is the first time that any such embedding was defined by explicit equations, or depicted by computer graphics. N-fold torus. In the theory of surfaces there is another object, the n-fold torus, often called the n-hold torus. Instead of the product of n circles, an n-fold torus is the connected sum of n2 tori. To form a connected sum of 2 surfaces, remove from each the interior of a disk and glue the surfaces together along the disk's boundary circles. To form the connected sum of more than 2 surfaces, sum 2 of them at a time until they are all connected. In this sense, an n-torus resembles the surface of n doughnuts stuck together side by side, or a 2-sphere with n handles attached. An ordinary torus is a 1-fold torus, a 2-fold torus is called a double torus, a 3-fold torus a triple torus, and so on. The n-fold torus is said to be an orientable surface of genus n, the genus being the number of handles. The 0-fold torus is the 2-sphere. The classification theorem for surfaces states that every compact connected surface is topologically equivalent to A, the sphere, or B, the n-fold torus with n greater than 0, or C, the connected sum of n projective planes with n greater than 0. Toroidal polyhedra. Polyhedra with the topological type of a torus are called toroidal polyhedra, and satisfy a modified version of the Euler characteristic, via E plus F equals 0. For any number holes, the formula generalizes to via E plus F equals 2 or 2n, where n is the number of holes. The term toroidal polyhedron is also used for higher genus polyhedra and for immersions of toroidal polyhedra. Automorphisms. The homeomorphism group of the torus is studied in geometric topology. Its mapping class group is isomorphic to the group GL, N, a Z, of invertible integer matrices, and can be realized as linear maps on the universal covering space Rn that preserve the standard lattice Zn and thus descend to the quotient. At the level of homotopy and homology, the mapping class group can be identified as the action on the first homology. Since the torus is an Eilenberg-Euro-MacLane space K, G, A1, its homotopy equivalences, up to homotopy, can be identified with automorphisms of the fundamental group. That this agrees with the mapping class group reflects that all homotopy equivalences can be realized by homeomorphisms every homotopy equivalence is homotopic to a homeomorphism and that homotopic homeomorphisms are in fact isotopic. More tersely, the map homeo, Tn, a she, Tn, is one-connected. This is a homeomorphism reduces to homotopy reduces to algebra result. Thus the short exact sequence of the mapping class group splits. So the homeomorphism group of the torus is a semi-direct product. The mapping class group of higher genus surfaces is much more complicated, and an area of active research. Coloring a torus. If a torus is divided into regions, then it is always possible to color the regions with no more than 7 colors so that neighboring regions have different colors. Cutting a torus. A standard torus can be cut with n planes into at most parts. The initial terms of this sequence for n starting from 1 are 2, 6, 13, 24, 40, a euro. See also, Notes, Nations de Geometria Analytica y Algebra Lineal, ISBN 978-970-10-6596-9, author, Kozak Anna Maria, Pompia Pastorelli Sonia, Verdengor Pedro Emilio, editorial, McGraw-Hill, edition 2007, 744 pages, language. Spanish, Alan Hatcher. Algebraic Topology. Cambridge University Press, 2002. ISBN 0-521-79540-0. V. V. Nikulin, I. R. Shafarevic. Geometries and Groups. Springer, 1987. ISBN 3-540-15281-4, ISBN 978-3-540-15281-1. Toroid Encyclopedia Copyright Die Forms Mathe Copyright Matix Remarkables, References, Harold A. Stein, Fitting Guide for Rigid and Soft Contact Lenses, A Practical Approach. St. Louis, Mosby. PA 16. ISBN A978-0-323-01440-3 Equations for the Standard Torus. Jim.uc.edu July 6, 1995. Retrieved July 21, 2012. Westerstein, Eric W., Torus, MathWorld. Oxford English Dictionary Online Poloidal. Oxford University Press. Retrieved August 10, 2007. As in The Road to Reality. Tymochko, Dmitry. The Geometry of Musical Chords. Science 313, 72 €74 doi, 10.1126/Science 1126287. PMIDA 16825563. Tony Phillips, Tony Phillips Take on Math in the Media, American Mathematical Society, October 2006, Filippelli, Gianluigi. Doc Manhattan, a flat torus in three-dimensional space. docmanhattan.fieldofscience.com. doi 10.1073/FNAS 1,118,478,109. Retrieved July 21, 2012. Mathematicians produce first ever image of flat torus in 3D mathematics. sci-news.com. April 18, 2012. Retrieved July 21, 2012. Mathematics, a first ever image of a flat torus in 3D, CNRS website, CNRS. Retrieved July 21, 2012. Flat tori finally visualized. Math Archive Lion 1 FR. April 18, 2012. Retrieved July 21, 2012. Westerstein, Eric W., Torus Cutting, Math World. External links: creation of a torus at Cut the Knot, 4D torus fly through cross-sections of a four-dimensional torus. Relational perspective map visualizing high-dimensional data with flat torus. Torus games, free downloadable games for Windows and Mac OS X that highlight the topology of a torus. Polidos, Czar. Copyright Quinn, Carlo H. Topology of a twisted torus, Numberphil. Brady Heron. Retrieved January 27, 2014. A.